So today we're very happy to have Zohar from the far land of Long Island to tell us about electrodynamics in 2+1D.
Yeah, thanks very much. It's really great to be here. Always very happy to come. Today, the first part of the lecture will be very basic about Maxwell theory in 2D, but you'll see that it has some very interesting aspects that maybe some of you haven't thought about, some very basic physics that can be explained without much background. And then we'll go to a slightly more advanced subject of electrodynamics in 2+1 dimensions, which is like Maxwell plus matter fields. And here, this problem is very, very old. It's something that people have been thinking about for over 40 years. It's connected to problems in particle physics. It's connected to problems in condensed matter. And I'll try to present some proposals for a solution. It's based on two papers that appeared on the same month, in the same month. One with Shai Chester from Imperial College, and then Ryan Thorngren, Thomas Dumitrescu, and Pierluigi Niero published a paper on the same subject, arriving at essentially the same final conclusion, though with some small differences about some small aspects. And now all of us are collaborating on making some variant of electrodynamics in 2+1 dimensions, and on the question of the forces between probe particles that I'll explain today. So that's the history. I'll start from Maxwell in 2+1 dimensions. The Lagrangian is very simple, but it has some interesting things that we will discuss. So that's the Lagrangian. It's a U1 gauge theory. So I'm specifying that it's U1 because the experts might know that there is a distinction between U1 and R gauge theory. But it's just a standard U1 gauge theory for now. This theory has two conserved currents. Is it visible here, by the way? It has two conserved currents. One, I'll just put a superscript 0 because in modern terminology it's a zero-form symmetry. It's an ordinary symmetry. And the conserved quantity is that. It's obviously conserved by the Bianchi identity. Not much to say. And the other conserved current has two indices. So in modern terminology, it's called the one-form symmetry. And it's just F mu. And this is conserved because there are no dynamical charges. So usually, ordinary charges act on local operators. So you expect local operators that would carry the set charges. So this theory, one thing that makes this theory slightly non-trivial is that it admits operators. These are perfectly local operators that depend on space and time. And they have an index n, let's put it here. And they carry charge n under this U1. So this U1 is called a zero-form U1 symmetry. This is a one-form U1 symmetry. So the charge of monopole operators under this U1 symmetry is n by definition. Okay, these operators are not easily visible from the Lagrangian. Does anybody need me to quickly explain what they are? How to construct these local operators, or it's well known to everybody?
Nothing is well known.
Nothing is well known. Okay. So if you make any combination out of the field strands, no such local operator will be charged under this symmetry. So the local operators that are charged under this symmetry are more exotic. They're similar to the disorder operator in the Ising model. And they're constructed in the easiest construction of these local operators is through the path integral. Let me just go to space-time notation. So it's some point x mu. So you take a point in space-time, you remove it in the path integral, you make a small sphere of size epsilon, and you just require the path integral to be such that the integral of the field strands is 2 pi n over this small sphere. And you just insert that condition into the path integral. You remove this ball, you make sure that on the boundary of this ball, namely on the two-sphere, the integral is that. Okay, it's a two-sphere with radius epsilon, and that defines boundary conditions. And this is a point in space-time, so it's a local operator. Okay, so, and these local operators are charged under the symmetry, and they cannot be expressed using the fundamental fields in no way. Okay, so these operators are very important in 2+1 dimensional Maxwell. They are local operators, so they can get an expectation value. We can study their correlation functions, and they're crucial. Yeah.
This is just like a monopole instanton, right? Like it's just you're in 3 dimensions. It's very related to that standard monopole solution, like Dirac monopole, correct? I mean, it has integer magnetic flux.
The Dirac monopole is a particle.
Yeah, but now you're in 2+1 dimensions, right? So now you're studying a different type of object, which has no world line, right? Because
So the Dirac monopoles we can more easily intuitively understand because it's a particle. This is this doesn't create a particle when you act on the vacuum.
it's more like an instanton, right?
Instanton is the Euclidean solution, something else.
Well, okay, right. But
This is
it's
a local
it's a point
operator.
thing, yes.
Condensed matter people call it disorder operators, though they also call disorder operators some various other things. We call it monopole operators. And the thing is that so the phenomenology of Maxwell theory is of course very easy. There is one particle which is massless, one massless particle. That's just what Maxwell theory in 2+1 dimensions is. But the massless particle is the so-called photon, but the photon has only one polarization. So you can think about it as a massless scalar. There is no distinction between a massless photon or a massless scalar in 2+1 dimensions. And a very wise point is that you can do a calculation and prove that these monopole operators condense in the vacuum. So actually the vacuum of Maxwell theory in 2+1 dimensions is order. There is order. And the order is only visible if you compute the expectation value of monopole operators. And when that means that the U1 symmetry is broken. So the U1 zero form symmetry is broken. That's just empty. It's broken completely. And therefore, by the Nambu-Goldstone theorem, you can think about the photon as a Nambu-Goldstone boson. So that's nice, because we don't have the same story. We cannot say exactly the same words in 3+1. The photon here is like Goldstone boson. Yeah.
So I can think about the scalar as just being, as just arising from dualizing f mu nu to d mu phi.
Yeah, you can say that since it's a scalar field, there is some. You could just say that I'm gonna write it as d mu phi.
Right.
And then you can say that you can try to express the Lagrangian using phi.
Right.
Instead of a gauge field.
And then the gauge symmetry has become a shift symmetry of phi. But I guess I was wondering, right? I mean, the phi is a shift symmetry, and I can think about that as coming from the gauge symmetry.
The shift symmetry is a global symmetry. So if you try to dualize, this is the shift symmetry is the U1 global symmetry. The gauge symmetry disappears because under duality, gauge symmetry is not a concept that carries over. It's a redundancy.
If I would like to think about the U1 versus R as a low energy theory coming from a non-abelian gauge theory, like SU2 broken down to U1.
Yeah.
How would these words go there?
If you start from a Georgia-Glashow type model, as you know, this quantity is not exactly conserved in the ultraviolet, because if you make some clamp of W bosons, they will carry this charge. You know what I mean?
Yeah.
So that symmetry is viewed as accidental or an approximate symmetry, and it's actually broken by small operators.
So you couldn't reformulate this language.
What I'm saying is that if you start from the Georgia-Glashow model, this symmetry is not expected to be exactly conserved, and therefore this cannot be exactly the Lagrangian. So what you actually get is you have to deform the Lagrangian by some small coefficient epsilon, multiplying M1 plus the complex conjugate. So the Georgia-Glashow model leads to not electrodynamics, not free Maxwell, but free Maxwell where the monopole operators are in the action. It's not an operator anymore. We can say it's proliferated. We say sometimes that it has proliferated, meaning that you had to add it to the action. So
This is kind of an explicit breaking.
yes, because you start from a microscopic theory where there is no zero form symmetry. So therefore, this is the effective theory. And this effective theory is very phenologically different from Maxwell because you have proliferated monopole operators. And it actually gaps the scalar. So this theory has a gap in massive bosons, not massless bosons. Okay? So there is a very interesting mechanism of giving the photon a mass in 2+1 dimensions by adding monopole operators into the action. We don't have such a thing in 3+1. In 3+1, the only way to get a photon is through the Higgs mechanism. But in 2+1, we can also add monopole operators. Or we can do Higgs mechanism. It's independent. Okay, so you can think about it in this way. Another important thing is what happens when this theory doesn't have dynamical charges, but you can put a dynamical charge of charge Q1 and another dynamical charge of charge Q2. These are just probes that you put into the vacuum as an experiment, and you can ask what is the energy or the potential or the force, and the energy, this is not the electric field, this is the energy. The energy is Q1, Q2 times the logarithm of the distance. So this is the distance. And this is just the familiar Coulomb potential in 2+1 dimensions. And the fact that it's logarithmically growing means the charges are confined. So charges are not good asymptotic states in 2+1 dimensions. So sometimes we say that the charges are confined because you cannot separate negative and positive charges due to the logarithmic force. It's not like a flux tube. A flux tube leads to a linear force, to a linear potential. Here, it's like a logarithmic potential, but it's still a flux tube of some sort. It's like some kind of diffuse flux tube. Okay. This is valid. Okay. Sometimes in modern language, people say that this means that the one-form symmetry is unbroken, but this is a subtle case because it does create one particle states from the vacuum. So it's kind of there is a little bit of semantic maybe disagreement on whether this should be called unbroken one-form symmetry or broken. Most people say it's unbroken because it's confined. So there are no asymptotic states. One last thing is that you could do R-gauge theory. You can also study R-gauge theory. Now this is for the advanced people in the audience. So in R-gauge theory, there are no monopole operators, and this is not a symmetry. I'm not going to explain this statement, it's just for the advanced people. And then Q1 and Q2 could be fractional, and this formula is still true. But then we don't have a clear interpretation of an Ambo-Goldstone story, because there are no monopole operators. Still, there is a massless field, but it's slightly more exotic. Okay, so these are just a few comments about R-gauge theory.
So just back to the U1, so you have the logarithmic, and how does this fit with the lattice picture of Polyakov, where you have also a linear potential?
No, in Polyakov started from the Georgia-Glashow model. So Polyakov had an additional term in the Lagrangian.
He did, but you can interpret his results.
You can interpret in modern language what Polyakov did, that the lattice generated an additional term in the Lagrangian. He didn't really start from Georgia-Glashow, he started from lattice gauge theory. And in lattice gauge theory, you cannot prevent these epsilons from being non-zero, at least in the old lattice models. There are, by the way, new lattice models where it is preventable. They're called Villain. But in the old lattice models, it was not possible to prevent these operators from appearing in the action. And if you repeat the analysis of, for instance, the correlator of two probe charges in the presence of this little perturbation, the force becomes linear rather than logarithmic, and you get something that looks more like actual confinement. That's number one. And number two, this scalar becomes massive. So, but today I'm going to talk about the theory without these perturbations. Also because nowadays it's possible to simulate on the lattice directly due to the Villain formalism advances in the villain properties, which allows to suppress monopoles.
When you rewrite the action in terms of phi, is the monopole operator just a vortex?
Cosine. It's a potential, it's not a vortex. It's just a potential, which is a cosine.
And this m can be written in a simpler form in terms of phi, or?
Yeah, they're exponentials of phi.
Yeah, just
So when you do n plus m pi, you get a cosine. And there's a simple way to see why that leads to a linear force. Because the probe charges in the scalar description, there are vortices, superfluid vortices, and then the vortex has to, I can explain to you later, but when you have a superfluid vortex, usually they experience logarithmic forces. Ordinary superfluid vortices, they have logarithmic forces, but when you add the cosine of the superfluid order parameter to the action, then you want phi to be like pi almost everywhere. But you cannot make it everywhere pi because there has to be a branch cut. So there is a small region in space where it goes quickly from being a pi to minus pi. And that's a small region in space, and that's the flux tube. Okay. Yeah.
So a generalized symmetries enthusiast would say, right, that the reason interesting things happen in 3 dimensions is because for d plus 1 dimension, for d greater than 3, like we're always dealing with just higher form symmetries when we're talking about Maxwell theory. But as soon as we go to 2 plus 1, right, now the magnetic symmetry becomes a 0 form symmetry, as you've said. And there's some vague understanding currently, which I don't think is quite fleshed out, about the robustness of 0 form symmetries versus higher form symmetries, infrared physics under symmetry breaking. I guess I'm just curious if you've thought about it from that point of view.
Well, clearly it's not robust here because the old lattice simulations did produce perturbations that break the symmetry. That's what you're referring to, I think.
Quantum perturbations, yes.
Hmm?
You mean, sorry, which type of perturbations are you talking? No, I'm just talking about.
Epsilon n plus epsilon
Yeah, yeah.
bar. So all lattice simulations couldn't simulate Maxwell theory. It sounds insane, but it's true. It was extremely difficult. You can ask Eliezer. He has many papers from the 80s on lattice simulations. It was very difficult to simulate this theory in the 80s because you always generated monopole operators and you couldn't see this phase of a massless photon and logarithmic confinement. Now it's possible. People have found a clever way to suppress the monopoles.
You could also have written a Chern-Simons square, right? Yeah.
You could, but I'm not discussing it today.
So this can be a leap. I mean,
I'm
it's
not
not
discussing. I'm only discussing today theories which have time reversal symmetry. So I'm not going to discuss Chern-Simons terms. Okay. So what is the business in? So what is the question in this business? The question is what happens when you graduate and go to QED. So the simplest, what is QED? It's 2 non-chiral fermions. So you add psi bar I, and I goes from 1 to 2. A covariant derivative psi I. You could also add masses. I'll put them in parentheses. M, I, J, psi, J, bar, psi, I. So 2 flavors. You need 2 flavors for this theory to exist, to be time reversal invariant, to be non-chiral. It's a little bit like the dimensional reduction of a Dirac fermion. Dirac fermion has 4 components. You reduce it to 2 plus 1, you get 2 plus 1 dimensional Dirac fermions. So this is the simplest possible non-trivial theory in 2 plus 1 dimensions. People often call it QED 2 plus 1. That's a notation that you will see in the literature. And why is this theory interesting for applications? So this theory is interesting for applications in 2 different fields in physics. One is in particle physics. It's been known for a while that if you start from QCD and you have a chemical potential for baryon symmetry, the physics, there's something that's called the Roberge-Weiss. Some of you know Roberge-Weiss point. So there is a long standing effort to understand the phase diagram of QCD at finite baryon density, like in neutron stars. And there is a very interesting work on conjecture of Roberge-Weiss about some critical points. And the effective Lagrangian is 2 plus 1 dimension because you're at finite density, there is some kind of dimensional reduction. So that's the connection to particle physics. In condensed matter, this model appears very naturally when you study Kagome lattices with Heisenberg models. It even appears in actual crystals. There are actual crystals in nature that are called Herbert-Smithites, and they have a very interesting, very similar theory to that. Sometimes they have 4 fermions rather than 2, but there are some mechanisms to get rid of 2 out of 4. So there are actual crystals in nature whose effective theory is very similar to that. And the U1 gauge theory in those crystals has nothing to do with the photon. It's not the physical photon. It's like an emergent photon that comes from the, degrees of freedom of electrons hopping between different atoms in this quartz, in this crystal. So there's a lot of interest in this kind of models in condensed matter.
No, just to understand, so in those theories, you don't actually have a field A mu, A mu is some
Emergent.
composite operator of,
It's
like in CPN
like if you go
models.
to long distances, okay, then you take this crystal, you cool it to 0 temperature, you go to long distance, and you try to ask what are the degrees of freedom. So you forget about electromagnetism. Electromagnetism is irrelevant. So the degrees of freedom are some Dirac fermions and the synthetic gauge field. They call it a synthetic gauge field. It's an emergent gauge field. It comes from
So it's a
the dynamics
composite of the other operators.
Yeah, it's like a composite of some fermions that hop between nodes of this crystal. It's an emergent gauge field. Okay, so there's a lot of work on that in both communities. Okay, so what do we know about QED in 2+1 dimensions? So if you take all the masses to be vanishing, so the most interesting point is when the fermions are light. So basically, conceptually, there are 2 things. If the masses are large, you can integrate out the fermions, and you land on something that you know. You land on Maxwell theory, perhaps with Chern-Simons terms. I won't go into that today, because it doesn't happen in this case. So if the masses are large, it's not a big challenge to solve this problem, because you can integrate out the fermions and you land on something quadratic. So we call that sometimes the semi-classical limits, or weakly coupled limits, and everything is understood about this.
But in this limit, this U1 is unbroken and you have the massless photon? No.
Yeah, roughly speaking, yeah. It depends on the mass matrix has positive and negative eigenvalues. So it depends on how many positive, how many negative eigenvalues there is. I can explain in more detail later. But if the eigenvalues are both positive or both negatives, you end up with a gap theory with just nothing. If one is positive, one negative, you end up with a massless photon. So, but this is easy to analyze. I'm just saying it's not conceptually difficult.
But the crystal was like a lattice regulator, which was hard to find.
The model, when this appears in condensed matter applications, the mass is set to 0.
Yeah.
So you're not in none of one of those semi-classical cases. And that's why it's an outstanding problem in condensed matter to understand what does it actually do. So this is not in the large masses. It's like, when you come to it, when you think about this problem as a theorist, you want some knobs, some handles. So you want to try to draw a phase diagram and try to patch it. So I use it a lot as like just a crux to understand what might be going on. But in condensed matter, pretty much nobody cares. They just care about the masses theory. So that's what appears naturally in applications.
But I guess related to the mass question, like in condensed matter, typically there are knobs we can tune.
Yeah.
Is there a knob in the case of this crystal that you can tune correspond to the mass?
Yeah. So I'll show you. So when the mass vanishes, this theory has a lot of symmetries because the 2 species appear on the same footing. So there is an SU2 symmetry, which is isospin. I'll call it isospin. Just rotate the 2 species of fermions one into another. Another symmetry that appears when the mass vanishes is time reversal symmetry, which they call particle hole symmetry. It's just exchanging psi and psi dagger essentially with some gamma matrix. And another symmetry is the monopole symmetry. So that symmetry is always there. It's because the Bianchi identity is satisfied. So if you want to go away from the massless point, you have to break some of those symmetries. So one way of going away from the massless point is to keep the 2 masses the same. So you have 2 positive eigenvalues, but then you destroy this. Another way to go away from the massless point is to keep P, but destroy the isospin symmetry by giving one positive mass and the other negative mass. So you can destroy the lattice symmetries a little bit and try to explore the phase diagram. But the most natural one preserves all those symmetries. Okay? So this is the most interesting theory, and there has been a lot of literature on that in high energy physics as well. So let me just go quickly review the history for you. I mean, I'm not the first person that thought about massless QT, obviously. There's been tons of work on that. So I'll just summarize what is the bottom line of a lot of research into that problem. So I'm just going to summarize this case, the massless case, which preserves all the symmetries. So starting from the 1980s to roughly 2016, 17, the widespread belief, based on some lattice simulations and some qualitative arguments of the Witten type, was that the fermion bilinear condenses. So this is going to be some scale squared times the Kronecker delta function. And therefore, people have been saying that SU2 isospin is spontaneously broken to U1 isospin, and therefore you have two numbers on both sides. And this idea is very prominent in particle physics papers because that's very similar to what happens in the standard model. You have some fermion condensate and you break the chiral symmetry. So that's what people have been saying. So that's one widespread conjecture. It was very difficult for me to understand what do these papers imply for U1 0, which is the Bianchi identity. I told you that in free Maxwell, this is spontaneously broken. It's very difficult to understand what was the scenario for that. Is that broken or not? Because this is uncharged under U10. You have to say, what about monopoles? It's unclear what they were believing is true regarding monopoles. Around 2017, 2022-23, a new story appeared. A new story appeared by condensed matter people and people from our and high energy physics people. People were saying that instead of symmetry breaking, people were saying there is no symmetry breaking, so they changed their minds. And they were saying that in fact it flows to a second order transition, namely a conformal field theory. So people said actually there is a conformal field theory in the infrared where this SU2, time reversal, and U1 combine into O4. So there is symmetry enhancement. So people were saying that perhaps there is symmetry enhancement, no symmetry breaking, and you have a non-trivial conformal field theory that we don't know about. This was a claim that was pursued for a couple of years. It passes many consistency checks. It's an interesting claim, but it was recently ruled out by numerical simulations and by the bootstrap. It's ruled out by bootstrap and numerical simulations. So at the end of the day, 2024, there is no clear idea of what's going on. So I'll tell you today what is our idea. Are there any questions about the history?
You said before that the term, the Maxwell term is an emergent term.
In condensed matter.
Yes.
Yeah.
Now, if I take a CFT, this cannot emerge because this breaks scaling variance.
No, this is the infrared limit, right? We're not, I mean, the ultraviolet Lagrangian is clear.
You're not viewing.
we're asking what is the infrared physics?
Okay. Okay.
So when there was a Hebrew University, this huge winter school, this was about this topic, this was the claim. And there were lectures about it. This was ruled out since. Okay. So,
So this is this neo-VBS transition that we talked about.
right, and people during that period also people said that the nel VBS antiferromagnet also exhibits the same symmetry enhancement and is in the same, and also but by now we know that such a CFT doesn't exist, at least not with the number of marginal relevant operators that we needed for this to make sense. So we decided to revisit this problem, and I think we found the answer now, finally. We have an answer that makes sense, passes consistency checks, and is very likely to be confirmed in the future, in my opinion. And it also leads to exotic physics. So I'll just tell you what we believe is the answer.
Sorry again, Joel, just pedagogically. So, was there, before people came with this new idea, was there any problem with this idea? Is there any intrinsic problem why this couldn't be the right?
So here, it's unclear what happens to this.
That's the issue.
What
Okay.
happens to the
To the
monopoles?
monopole.
Are they condensing or are they not condensing? Are there 2 non-Bosons bosons or 7 or 3? It's not clear.
Probably not.
It's not clear. I don't think there was any issue with that. In fact, our answer is closer to this than to that. A small issue with that is that lattice simulations could not confirm this scenario directly, because it was very difficult to simulate on the lattice a model without monopoles, as I already said a few times. So people have struggled with that for ages. But as I said, now there is some hope. Okay, so let me tell you an answer that makes sense. And I'll first describe the answer and the interesting physics that it leads to, and then I'll explain maybe how we arrived to it. So the answer is the following. So the answer is that the low energy limit of QED, QED, 2 plus 1, when it's massless, with massless quarks, is given by a nonlinear sigma model with target space S3. So let me write the Lagrangian. The Lagrangian is dg minus 1, d2x dt, and g is an element of SCO2. So this is the first piece of the answer, that in fact there is a nonlinear sigma model with target space S3, and a very convenient way to express such a sigma model is to write this minimal kinetic term with G an element of the SU2 group. Another important element in the answer is that since pi 3 of S3 is Z, when you say that the low energy limit is a 3-sphere, you have to specify one more piece of data, because there is a topological term in the sigma model. So there is a term at theta times gamma, where gamma is a topological term. We'll just write it down. It's just the winding of space-time into the target space. So gamma is 1 over 24 pi squared integral of d2x dt trace, oh I forgot to write trace, I'm sorry. It's of course matrices, so I have to trace them. I have to trace here. A trace of g minus 1 dg, g minus 1 dg, d minus 1 dg, and then there is an epsilon tensor. So this is an interesting term that you can add to the action in 2 plus 1 dimensions, and the coefficient is a theta term. It's not visible classically. The equations of motion don't care about theta, and we have to choose theta correctly to specify what is the conjecture, and we choose theta equals pi. Theta, it's a very nice choice because of this fact. There is time reversal symmetry. So under time reversal symmetry, theta goes to minus theta. So there are 2 possible choices, theta equals 0 and theta equals pi, mod 2 pi. All these thetas are defined mod 2 pi because this integral by itself is an integer. So since the integral is an integer, it's just the 3/3 homotopy. Theta is defined mod 2 pi, so there are 2 choices which are in time reversal invariant, pi and 0. So you have to decide, is it 0 or pi? and the only thing that makes sense is pi, because of some anomalies that I'm not explaining. There are some generalized symmetries and anomalies, discrete symmetries and anomalies here that force it to be pi.
But once you decided to add this term, it could have been anything. The question is, what is it
In QED.
equivalent to?
No, what is it in QED? I'm talking about a specific model. No?
Yeah, but you could look at the nonlinear sigma model and ask what other three-dimensional model it could represent.
Right. But I'm trying to determine the infrared
That's
limit
clear.
of massless QED. And I'm just saying that there's a lot of details that I cannot explain that are too advanced or too technical, there are 2 anomalies here. Okay, so maybe for the advanced people in the audience, I can say that the symmetry is not really SU2 times U1, as I've been saying, it's actually that. And time reversal is not a direct product, it's a semi-direct product, and there is some 2th anomaly. And to reproduce the 2th anomaly, you have to fix theta equals pi. And a calculation that we did in the appendix of the paper shows that it actually does reproduce the anomaly. It's one of the key consistency checks. Yeah.
So this term it's a higher derivative term, but it doesn't affect the equations of motion. So it's very much like Gauss-Bonnet in 4 dimensions and EFT of gravity.
Yeah.
So you could ask that's a meaningless question in 4D, but in higher dimensions I can ask what's the Gauss-Bonnet coefficient in EFT of gravity in some UV completion. Can I ask the same thing here if I'm reducing to 2+1 dimensions from some higher dimensional theory that's complete in the UV and it generates this at low energies under dimensional reduction, I can ask what is theta in realistic
Yes, so
conditions.
if you look at the problem of QCD at finite variant density, like in neutron stars, I haven't published it or checked super carefully, but it's very clear that theta has to be pi, also in this context. It's very clear because there is a similar anomaly and there is some. So I think yes, you can get it from higher dimensional theories at finite density or finite temperature.
Are there also at one loop, are there epsilon over epsilon effects in the way of other evanescent operators if you do this in dim reg in 3 minus epsilon dimensions?
Oh, I haven't thought about that.
Because the same thing happens with Gauss-Bonnet in 4D in gravity.
I know.
And I'd expect there to be epsilon over epsilon.
Yeah, I understand, but we didn't try to renormalize this theory or something like that. It's just the classical effective field theory at low energies like ion physics.
So what's the difference in the physics between theta equals pi and theta equals 0?
Let me think. I mean, you're not gonna see a big difference in the. You're not gonna see a big difference for simple local experiments. There are still gonna be like 3 Goldstone bosons moving on the 3 sphere. The differences will be very subtle. Maybe the free energy density will differ a little bit. The free energy density will probably depend on theta in some subtle way. Well, I didn't say that. The free energy density probably depends on theta. I have to check. I'm not sure. And it also affects the theory maybe with some chemical potentials. Yeah, I don't really know. That's the short answer. It certainly modifies the path integral completely. It's similar to the Aronoff-Bohm theta angle. When we just do quantum mechanics of a particle around an Aronoff-Bohm solenoid, so quantum mechanics of a particle that, just like undergraduate particle moving on a ring, you can say the Lagrangian is q dot squared, where q is the azimuthal angle. The way we model a solenoid, a Aronoff-Bohm solenoid, is that we added theta times q dot, which is total derivative. So what does it do? It modifies the energy spectrum, right? So the energies are like n plus theta squared. So you can see the Aronoff-Bohm solenoid in the energy spectrum, and modifies the partition function. It modifies the theory when you couple the translational symmetry to a chemical potential, but it doesn't do much, in some sense. So take it similar here.
I mean, in the Schwinger model, it makes a very big difference.
That's because that theta angle appears in the UV for the electric field. That's the theta angle for the electric field. This is the theta angle that appears in the infrared limit of QED. So it's an effective filtering theta angle. We're not trying to now flow to some new effective filtering from here. This is like the end of the story. So it's more like the theta angle in an Aronoff bond. So I think it has slight effects, but I'm not sure exactly which ones are the key slight effects to try to calculate.
This is theta or theta over 2 pi? In the sense where the spectrum repeats itself?
Yeah. It's periodic in 2 pi because this integral is an
So
integer.
there in the energy spectrum, it's probably theta over 2 pi.
Oh my god, yeah. Yeah. Very good. So there must be some similar things here. The spectrum on the finite volume will see theta, but I don't believe anybody has calculated it.
You can also put a boundary and see how.
Yeah. I don't believe anybody has calculated. Okay, so this is the proposal, and now I'll explain what is what phenomenology does it lead to. So I'll just write the metric on the trees here. It's useful to understand the geometry. This is just the usual metric on the tree sphere. So you can ask, where is U10? So I complained that in the past people didn't say what happened to U10. So clearly here we have 3 Goldstone bosons because we have a 3 sphere. So U10 and SU2 are both completely broken. That's our scenario. So there is monopole condensation, fermion bilinear condensation, everything is broken, and they lead to a 3 sphere, a group manifold. And you can ask, where is this embedded in the 3 sphere? Where is the Goldstone boson that has to do with the monopole symmetry? And it's this guy. So we claim that F mu nu epsilon mu nu rho in the infrared flows to deep side. Okay, so the Hopf circle is the shift symmetry from this dual scalar. So when we discussed Maxwell, there was a dual scalar, as you said. Here the dual scalar is the Hopf circle. That's claim number 1. And this leads to interesting facts about the force between.
Sorry, but just a silly question. Here you have U1 crosses U2 is fully broken.
Yes.
So don't you expect 4 Goldstone bosons?
Oh, sorry. Of course, yeah. I'm very sorry. It's broken to U1 diagonal. I'm very sorry. So you can say that the monopole vev and the fermion vevs are aligned. That's like the alignment from the 80s in QST. So, what phenomenology does it lead to? So let's consider the force between probe charges. I'm going to consider the force between probe charges Q1 and Q2 as before. And we can ask, what do we expect? Here, it's convenient. How can we compute the force between Q1 and Q2, given that the low energy theory is this 3-sphere sigma model? So the point is that, like in Maxwell, we can use the fact that if you go to the scalar description, a probe charge is like a superfluid vortex. So this is a superfluid vortex in psi, and this is another superfluid vortex in the Hopf circle psi. But on the 3 sphere, as you know, every cycle is contractible. Every cycle is contractible. So in Maxwell theory, we had found the logarithmic force because the circle that is dual to the photon is non-contractible. It was just S1. But here the sigma model is 3-dimensional sphere. So the Hopf circle is contractible, and therefore, to minimize the energy between such superfluid vortices, so you have now superfluid vortices for a contractible cycle. So clearly, energetically, they're going to contract. we haven't finished doing this computation, but it's very clear that psi is just going to contract, and there is not going to be long-range force. So there is screening. So the model is screening the electromagnetic force. So there is no more logarithm. I believe the force just goes to 0 at long distances, but we haven't finished computing. I have one more comment about the phenomenology, unless there are any questions. So one thing that makes this model even more exotic is the following thing. Let's go back to Maxwell, but now we will add massive charges rather than light charges. So that's supposed to be very easy. And let's ask, what is the force between Q1 and Q2? So because there are massive charges, you expect that there is no long-range force. So the logarithm goes away. The way it comes about in calculations is that you dualize the photon, you get the scalar, so it's a superfluid vortex. But the massive charges mean that the superfluid also has dynamical vortices. So a dynamical vortex from the superfluid can come close, screen it, and you have vanishing force. So here the force will be 0. Because dynamical superfluid vortices can screen this vortex. But in Maxwell theory with massive charges, you can introduce fractional charges. So let's say Q1 and Q2 are fractional. Then this vortex is a fractional vortex. And then dynamical vortices from the superfluid cannot screen it. So I claim that in Maxwell with massive charges, integer charges are screened. That's just a summary of what I'm saying. Integer charges are screened. There is no logarithm. That's what I mean by screened. There is no logarithm in the energy. But fractional charges are unscreened. That's just the property of Maxwell theory with some heavy charged particles. So there is a logarithm. So we can ask what happens in our model for fractional charges. So here, fractional charges mean that the vortex of the Hopf circle is incomplete. It's a fractional vortex. But that is also contractible. So on the three-dimensional sphere, even any loop is essentially contractible by some continuous change, bringing it to the South Pole or the North Pole. And therefore, they are still screened. So even fractional charges are screened. And that is really what makes this model different from anything that I have seen before in 2+1 dimensions. Because the idea that integer charges can screen fractional charges is something that Coleman has found in 2 dimensions in the Schwinger model, but it's not been considered as a possible outcome of any of these models in 2+1 dimensions. It was thought to be a particular phenomenon in 1+1. But I think in this model it does happen. So I think in QED, there is screening of fractional charges as well as integer charges when the charges are massless. So this is like Coleman's old mechanism in 1+1 that seems to be operating in 2+1.
So if I would be in 4 dimensions, then I would say, let's take an abelian Higgs model.
Yes.
Then I would say that all charge is screened.
Yes.
Okay, now in 2 dimensions, this Higgs and confinement gets all entangled with each other. But so you say that in 3, it's somehow an intermediate case between the 2. Is this, could I mimic this by a Higgs phenomenon?
Can you mimic that by Higgs phenomenon? Let me think what exactly is the question. Let me try to process it. So, so in 1+1 dimensions, if you look at the Higgs mechanism, then fractional charges are confined.
Because of instantons.
Because of instantons.
Yes.
Coleman's discovery was that fractional charges are deconfined. In the limit of the deep Higgs web, or in the limit of massless quarks. It's the same thing.
Or theta equals
yeah, so it's very special.
Yes.
And it's a phenomenon that has only been seen in 2+1 dimensions. Because here I'm saying the same seems to be happening in 2 + 1 dimensions, that in the limit of massless quarks, we see that fractional charges are screened, or very light quarks. So I think it is different. And also you see that it's also intuitively weird because there are only integer charges in the theory. How can a screened probe charge screen? How can you cancel the fractional number?
Condensation by making it an ill-defined quantum.
Yeah, so something like that is happening here.
That's why I said it's.
Yeah. So it is definitely similar to 1 + 1. So I'll just write it for the record. It's like Coleman's discovery in 1 + 1. Okay, so these are some comments about U1 gauge theory. I'll make, as before, quick comments for the advanced people or the experts in the audience about R gauge theory. I'm making comments about R gauge theory because it's a little bit easier to simulate on the lights. So I have to specify what people will see. So in R gauge theory, there are no monopoles. So you might think that this whole story with the 3-dimensional sphere is not going to be relevant because monopoles cannot condense. Now I'm going to say, just for the advanced people, what is actually happening is the following. So you can go from U1 gauge theory to R gauge theory and back and forth by some kind of special procedure that's called flat gauging. And it's very clear that fundamentally nothing can change by doing flat gauging. So if there are 3 Goldstone bosons in the U1 gauge theory, there cannot be 2 Goldstone bosons in R gauge theory because they are very similar things. What actually happens is that when you do this flat gauging and you follow through this whole chain of reasoning, you get the same S3 signal model with theta equals pi, except that psi is gauge equivalent to psi plus a constant. That doesn't mean that psi disappears. It's only a gauge transformation that's x independent. So you gauge away the 0 mode. So you get some kind of special 3-sphere where the 0 mode of the Hopf circle is absent. But all the non-trivial modes with Fourier modes of the Hopf circle are present. So it's going to have the same free energy, essentially 3 Goldstone bosons, but just one of the Goldstone bosons is slightly non-geometric. So you just get one Goldstone boson that is slightly non-geometric in our gauge theory, but everything else that I said basically stays true. So U1 and R gauge theory are very similar, except that S3 turns into a slightly non-geometric thing.
So it will change the nonlinear signal model character?
It just introduces, it just says that psi and psi plus any other constant are gauge equivalent. But the constant cannot be space-time dependent. So it's not like removing psi. It's just removing the 0 mode of psi. It's a non-local field theory. It's a somewhat non-local field theory, but very mildly. And so that's the prediction for R gauge theory. It's essentially the same, just slightly non-geometric. Okay? And yeah, so that's more or less the proposal for this model. Hey, there are any more questions? I'm almost out of time, so.
One question, I forgot the key, I missed the key point of the talk. So how do you argue that you get that sigma model? You have the symmetries?
Oh, I haven't explained it at all.
Okay.
I just said that this is the proposal and I explained the phenomenology that stems out from the proposal, but I haven't explained how to derive it. So there's no way to derive it except to prove it in the computer or prove it in condensed matter simulations. The best you can do is to make a proposal that's compatible with all the symmetries, all the anomalies, and it embeds nicely into some phase diagram. So that's what we did.
And why the CFT proposal of a few years ago is instead proven?
It was disproven by the bootstrap. It just turns out that such CFTs don't exist. So they wanted a CFT with some concrete properties, and there are no such CFTs. People have just disproven it. The best paper on this is by Jing Li from, I think, 2023. He gave a very beautiful summary of the bootstrap bounds, and they're incompatible.
Can you remind which aspect of the bootstrap is incompatible?
So the conjecture was that the low energy theory is a CFT with some operators that transform under O4 global symmetry. It was supposed to be enhanced to O4. And the key thing was that this is an exotic non-Landau-Ginzburg CFT because it doesn't have O4 singlets, which are relevant. Usually Landau-Ginzburg CFTs, like vector models, they have phi squared kind of operators that are relevant. That one was supposed to not have any relevant O4 invariant operators because it just doesn't fit into the discussion. And in particular, you can see in this paper that there is no such thing. There is no such thing. This is a very natural question for the bootstrap to ask, are there CFTs with A, B, C properties and no relevant operators which are singlets? And it was disproved.
So if there is a singlet, it has infinite height, or?
Oh no, they just wanted it to be relevant, but there is no such CFTs, and so given that fact, it's not possible to understand how it can be relevant for this particular model, because if there is a relevant singlet, you can add it to the action, and it may just flow away from the CFT. There is no reason why would you hit that CFT if it's an unnatural. It's tricritical essentially. So essentially, the bootstrap proved that if there is such a CFT, it has to be tricritical or multicritical. And so, how can you flow to it without tuning? On the other hand, QED does not have
fine-tune.
no, but QED doesn't have 3 parameters. So there is nothing to fine-tune. You're just like setting massless QED, doesn't have a single free parameter. So how can you hit a theory with an enhanced symmetry if the whole thing is multicritical? But now, of course, there is a follow-up discussion also after this paper that we put out, because there is a version of QED with 3 parameters that's called Gross-Navet QED. So that might maybe flow to such a putative CFT by fine-tuning.
So we didn't expect, so I was going to ask about the gross level deformation, but we didn't expect it to do something like deforming S3 by deforming the base, by keeping the hot vibration. So a version of the proposal should work for that case as well. You do turn on
But
the
then there is another scalar, no? Gross-Navet is another scalar field, the Habermas-Ratanovich field.
Yes, yes.
So maybe you want to add to that story one more scalar. We have to talk about it later.
Okay. Yeah. I have a question more related to the reason that you also presented the R-gauge version of the story, right? So if you understand correctly, that case can be simulated with current technology on that.
Yes.
And you have this proposal that there will be these 3 ghost-on bosons. So can that be already tested?
Yes.
And that's confirmed?
No, it can be tested.
Okay.
I assume it will be confirmed soon.
Is someone doing that?
Not me. Somebody will do it. I mean, it's an obvious question. And now that they know what to look for, they'll check.
Okay.
Somebody should take the speaker
Yeah,
first.
but one last question though. This is SU2 or SU2 over Z2? I mean, the G, does it live on the universal cover?
Here G is in SU2, but the global symmetry of such a sigma model is SU2 cross SU2 mod Z2. That's what you were asking.
Yes, but G, so could you take it into SO3 instead of SU2?
Oh, no, that wouldn't work. That wouldn't work because so if you looked at the sigma model with target space S3 mod Z2, so there are 2 possible sigma models. One is with target space S3 and one with target space S3 mod Z2. The sigma model with this target space has symmetry SU2 cross SU2 mod Z2, and that's isomorphic to SO4. And SU2 times U1 is a good subgroup, and that's the symmetry of QED. That's the symmetry of QED. So the one that I wrote is just a symmetry enhanced version of the symmetries that we know that exist. In this one, I think the global symmetry would be SO3 cross SO3, and there is no center. That is not a subgroup. So SU2 times U1 mod Z2 is not a subgroup of that. So this doesn't make sense.